Hi, everybody. My name is José Carlos Carrasco, and I'll be presenting part of my research work. In this case, the title is Prediction of Social Ties Based on Bluetooth Proximity Time Series Data. Just to introduce myself a little bit more, as I said, my name is Carlos, and I'm a researcher at the Barcelona Supercomputing Center. We currently host Mare Nostrum 4, which is one of the largest and most powerful supercomputers in Europe. Um, I work at the Computer Applications in Science and Engineering department, in which we pretty much focus on projects that deal with industrial applications mainly, but we also do other types of projects. Uh, I would like to start my presentation by explaining more or less the context and the problem that we want to tackle. And as I said, I would like to start with a network of people, also known as a social network. And we're pretty familiar with the term social network, but we usually associate this term to the online social networking websites, such as Facebook, Twitter, Instagram, and all those online networking websites. But when we talk about social networks in our context, it refers more to the human networks. And that's what we call social networks. Before the introduction of these online websites, uh, typical studies of how humans interacted and organized themselves included different dimensions, such as the anthropological dimensions, psychological dimensions, social dimensions. But for this particular project, we're going to focus on technological dimension. And what I mean by technological dimension is how we approach the discovery or the uncovering of social structure. Okay, uh, there is an intrinsic social network that we know that exists. That is the real social network. Social structure is important because it reveals how we interact and how we organize as humans. And when we talk about social links or social ties between two people or two persons, uh, we refer to a specific dimension that links two individuals based on some evidence that we have. In this case, as I said before, we have plenty of research related to online social networks, but very little is done at the physical level. Okay, uh, when we talk about different dimensions, one of them is also the virtual dimension or the online evidence that we have of social links. Okay, but as I said, these online social networks are nothing more than an inaccurate subset of the actual human network. That is, the 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 links formed at the physical level are not accurately represented most of the times by the virtual versions of the social network. So why is it inaccurate to say that the online version of the social networks capture the intrinsic social network? Why do we say it is inaccurate? Pretty much because it is based on self-reported data, and we know that self-reported data might be uh, I mean, it pretty much depends on the mood, and many other external factors that might suddenly change. However, in this research work, we seek to uncover social structure, which is the same as uncovering social ties. Okay, to do so, we're going to use, or actually, we use Bluetooth detection of proximity events to analyze the relationship between physical proximity and social linkage. So we're going a step forward as compared to the virtual social networks. And we use Bluetooth because it captures encounters in really like small, short ranges. Discovering social links has important implications and applications as well, especially now that we're dealing with our health emergency, something that we all know about, which is the COVID emergency that we have, well, it is important to track these links in order to do something about the disease. And as part of the related works, we have different approaches. One in which we have online communications, which are analyzed in order to discover social ties. In this case, when we talk about online communication, we refer to the virtual social networks. For example, data that can be extracted from online social networking websites. But there are other approaches that are like a mix of online communication as well as physical proximity information. Some studies pretty much combine both of these sources of informations. But in our case, we focus mainly on the physical clues. That's pretty much what we're doing. We want to know to what extent are we capable of uncovering social ties based only on physical proximity and nothing else. We seek to uncover social ties by exploiting only physical proximity captured through Bluetooth-enabled devices. So the question we ask ourselves is whether or not we are able to uncover such social ties solely from Bluetooth traces. And for this, we design a methodology which pretty much consists of four main steps. Okay, the first one being the pre-processing phase, in which not only do we prepare data, but we also solve some problems that we found in the data set, which is related to the encounter and friendship asymmetry. And for this, just going a step back, the data that we're using comes from the social evolution dataset collected by members of the MIT research from an MIT research group. But although they collected many kinds of information, like for example GPS, Bluetooth, they applied many surveys and so on. We're only focusing on the Bluetooth information because it gives us information about proximity, physical proximity. And going back to the steps, building social proximity maps, what we do in that step is we provide useful insights for choosing the features needed in the next step, which is the extracting feature encodings. As part of this research work, we have prepared three different types of encodings, which we're going to explain in the next slide. And these encodings capture different aspects of social relationships. And what they do is they serve as the basis for training our social type predictor. And lastly, the last step of our methodology is the building of social network, in which we use supervised learning to identify the underlying social network. We have used a pretty useful tool to reveal patterns of encounters between pairs of people, and we call them social proximity maps. In our image on the left of the screen, what we see is 4 different social proximity maps corresponding, the first one, for example, to 2 people that are close friends. And what we see is the red areas correspond to the days and times in which there was no interaction between those 2 people. The green dots in the proximity map refer to those hours of and the corresponding day in which 2 people encounter. The encounter was reported by both devices, and the white dots in the proximity map represent those moments in time in which either one or the other reported the encounter, but not both. And the way we organize our proximity maps is in each row we have a day of the week, and each column corresponds to hours of the day. So if we take a look at, for example, the letter A of these proximity maps, what we see is close friends have a lot of interaction, as we can see in the figure. But if we take a look at, for example, the letter D, which is corresponds to Twitter interaction only, there is no physical proximity. Only, I mean, these two people interact through online social media, in this case, Twitter. We see that physical proximity it's pretty much irrelevant. Okay, so this is just to give us an idea, and what we seek with social proximity maps is to give us an idea of which features do we need to consider for our analysis. In order to do this, we also have created three different sets of what we call the social encodings. So that the first one, which is kind of like a brute force approach, it's in this one we use full-time series, and it's like taking our social proximity map and unfolding it. So what we have in these unfolded matrix, we have time series full of zeros or ones, in which zero it represents the lack of encounter and one represents an encounter. The second social encoding that we're going to analyze is encounter, I mean, which would take in consideration encounters and the time at which they happen. For this social encoding, we have a total of 18 features, including the total number of encounters between a pair of people, the number of weekday encounters that they recorded, number of weekend encounters, number of morning encounters, lunchtime encounters during lunchtime, encounters during the afternoon, evening, and early morning. And finally, the third social encoding that we used, we represented as a frequency of encounters, but also adding the total duration of each one of those encounters, the average duration, as well as the weekly encounters. So pretty much what we have for as part of our results, for each social encoding, we have used 4 different algorithms: the support vector machines with different parameters, the K nearest neighbors, penalized discriminant analysis, and linear discriminant analysis. We are using supervised learning approach, and as I already explained, the label was collected as part of the social evolution dataset. So they gave us the labels of the social link and also the type of social link between two people. Now, what we did, part of our analysis, we analyzed both cases in which we tried to identify a multi-class label and a binary class label. So for the multi-class, our results are very poor. The performance is very poor. So what we can conclude out of this is that our approach doesn't work for multi-class. That means it doesn't work if we want to, if we're trying to identify a specific type of relationship between these two persons. Furthermore, if we just try to identify whether a social link exists or not, we have pretty good results. And if we take a look at table 1, for example, we see the performance for the full-time series approach. And as I said, this approach, in this approach, we consider not only encounters, but also the lack of encounters. So this one showed the best performance when compared to the other 2 social encodings, but table 2 shows the results of one of the second social encoding, in which we use encounter plus time. In this case, we also get good results, but what we find is that there is some discrepancy between the different algorithms. So at the end, we just took the best performance of each one of the social encodings and the different using the different algorithms. In this case, what we found is that for the full-time series performance, what we found is that pretty much all the algorithms perform pretty similar. On the other one, the results, the performance of different algorithms is different. It varies from algorithm to algorithm. As part of the conclusions, we can say that social encodings were used to predict the presence and absence of relationship with pretty high accuracy. Other than that, I would like to say that uncovering the specific type of relationship, it's still an open question, at least using our approach. Full-time series shows very good performance for most of the classifiers considered independently of the classifier used, which is pretty good news. That means that considering lack of interaction between two people, it gives us a lot of information in order to classify or identify social linkage. On the other hand, encounters in time, it gives us some features that provide good predictive power, but they're linked to specific classifiers. And as I said, some classifiers didn't perform as well using this social encoding. So we still can say that we stick with the full-time series approach. And we have successfully shown that Bluetooth-based proximity clues by themselves account sufficiently for the presence and absence of personal relationships. That is, if we just seek to discover social ties, whether or not it exists, our approach is it shows very good performance. But the specific type of relationship between two individuals is not predictable with the spatial temporal features that we considered in this work. Thank you for watching. If you have any questions or any concerns, you may contact me via email, jose.carrasco@bse.es.